All right, welcome back, everyone. This is the last lecture of Peter, and thank you, Peter. Here you go.
All right, thanks, Haluk. Okay, so the goal of this last lecture is to say as much as possible about classification of the temporal representations, which is what we've been working towards. We've been developing some theory, and now that's all going to be put together. And then in the next lecture by Bram, that'll be used to describe the reduced Higgs algebra of the group G, the semi-simple group G. Okay, what I'm going to talk about today is first about intertwining operators, which are a tool to see if certain induced representations are irreducible and which ones are are equivalent. Then I'll talk about the classification of almost all temporal representations, an open-dense subset in a sense. And in the last bit of the talk, I'll look at the case where an induced representation may be reducible and look at how it decomposes into irreducibles to work towards at least a complete classification of temporal representations. Just a quick recap of what we've seen. We looked at a real semi-simple Lie group G, so it's inside GL and C, closed subgroup, closed on a conjugate transpose and finite center. And the temporal representation that we looked at were the ones that occur in the Branch-Well decomposition of the L2 space with the left and right actions. Part of those is the discrete series, which are the direct summons of this space. We've classified them when they exist. And they exist when there's a compact Cartan subgroup. And then in the second lecture yesterday, we looked at cuspidal parabolic subgroups, which look like M times A times N, where M is roughly speaking of the same type of group as G. A is a vector group, an abelian non-compact group. And N has a nilpotent Lie algebra. And this is a cuspidal parabolic. And in our construction, we end up with a cuspidal parabolic, which means that M has discrete series representations, which we're going to use today. Then given a unitary representation of M and a unitary representation of A, we can apply an induction procedure to get a unitary representation of G, which is noted by this. And that's what we'll be using today. Okay, so the goal is to look at the classification. And relevant questions when we look at classifying temporal representations are, if we use these induced representations, is that enough to get all the temporal representations? And that's the answer turns out to be yes. Two other questions are, if we have these induced representations, when are two of them equivalent? And which ones are irreducible? Now, I'm going to mainly be talking about the second 2 points. For the first point, I'm just going to use a theorem. And the second 2 points can be answered with intertwining operators, which is what the most of this lecture is about. All right, so intertwining operators. They're important because of Schur's lemma, which I'm going to state now. First of all, an equivalence of two representations was defined as a unitary isomorphism between the spaces that intertwines the two representations. So by definition, for equivalence, intertwining operators are important, but they're also important for irreducibility or how they reduce when they're not irreducible. We look at this space, the bound operators between two representation spaces, so that they commute with the representations in this way, so they intertwine the two representations. And that space is denoted by this, a little bit like the fixed point algebras that Bram talked about yesterday. When the two representations pi and pi prime are the same, then we are up with an algebra of the G equivariant bound operators from H pi to itself. And a basic but very important fact is Schur's lemma, which says two things. If pi is irreducible, that's what I mean by G hat here, if pi is irreducible, then the intertwining algebra is one-dimensional, just contains the multiples of the identity operator. And the second property is if we have two different irreducible representations, pi and pi prime, then if they're not equivalent, this space of intertwining operators is zero. And if they are equivalent, then the space is one-dimensional. As I just said, By definition, if they're equivalent, there is a unitary intertwining operator, so the space has to be at least one-dimensional, but it's also at most one-dimensional, is a statement. Okay, here's the lemma again. Because this is important and also the proof is relatively elementary, I'm just going to make a few comments about the proof. First of all, for this statement here, that the intertwining operators from H pi to itself are just multiples of the identity. This is easy to see in the finite dimensional case where we have a self-adjoint intertwining operator T. Because for a self-adjoint intertwining operator, we can in the finite dimensional case, we can take the eigenspace decomposition, and every eigenspace is an invariant subspace. And by definition of irreducibility, all the invariant subspaces are either zero or the whole space, and that means there is only one eigenspace, and that means the operator is a multiple of the identity. So in that special case, the proof is linear algebra. In a more general case, where H pi may be infinite dimensional and T may not be self-adjoint, you do two things. You decompose T into self-adjoint operators in the form A plus BI. And instead of eigenspaces, use spectral projections, and the argument still applies. So the argument is, it's very pretty general functional analytic. For the second statement, for this space, this just follows from the fact that the kernel, if you have an intertwining operator between H pi and H pi prime, the kernel of T and the image of T are invariant subspaces. And then again, by irreducibility, they have to be either zero or everything. And by going through the four possibilities, you find that this is true. So that's why Schur's lemma is true, and that's the basis of everything about using intertwining operators. Here's a specific consequence of Schur's lemma. In the case where we have a finite number of inequivalent irreducible representations of G, and we form this direct sum. So we take mj copies of every pi j. This is a direct sum of mj copies of pi j. We add them together and we call this pi. Then Schur's lemma says that the algebra of intertwining operators on that direct sum is this direct sum of matrix algebras for every pi j. So to begin with, between two equivalent pi j's, we have no intertwining operators. That's the second part B of Schur's lemma. Within every pi j, so within every mj copies of it, we get this matrix algebra, because between every copy of the pi j's there's exactly one dimension worth of intertwining operators. So this is a very explicit way of writing the intertwining bounded operators on a finite direct sum of irreducible representations. And this says that if we have a finite dimensional algebra here, then we know exactly how H pi decomposes into irreducibles. A priori, we may not know what the pi j's are, but we know how it consists of a combination of different irreducible representations and then the inequivalence of the two, and how many copies of each we get. So yeah, computing this algebra is important for seeing how a finite direct sum decomposes into irreducibles. Okay, so I'm now going to work towards constructing specific intertwining operators between different induced representations. So this again starts with a Castrol parabolic P, which is MAN. And we applied unitary induction to tensor products of representations of M and representation of A. For the construction, we now need to go beyond unitary representations of A. So we're just going to slightly extend the definition. We're going to start with an element Xi, which is a real value linear map from the Lie algebra A to the complex numbers. And then we can define representation of A by this formula, by exponentiating as we've done before. But now we haven't assumed that Xi is imaginary value. If it's imaginary value, this is unitary. But now it's not unitary in general if Xi has non-zero real part. By the way, often psi and nu are called by the same letter. I'm just using different letters now just to make the distinction here. Okay, so now we have a unitary representation sigma of m and a possibly non-unitary but still inducible representation mu of a. Oh, I'm using some. What we'll use is an action of this group on representation sigma and mu of this type. So the group, the normalizer of A in K, this acts on these two representations sigma and mu. And that's because if W normalizes A, it also normalizes M. That's just a quick argument. If it normalizes A, then conjugation also preserves the centralizer, and hence the Lie algebra M, and it turns out also preserves the group M. So we can let it act on these representations by conjugation on the arguments, and that gives us new representations: W acting on sigma and W acting on mu of M and of A. Now this group is generally infinite, but it turns out that this action descends to a finite quotient of that group, namely this one. This group here will be important. The quotient of this nk of A by the intersection of K with M. So here, I should have probably reminded you, K is a maximal compact subgroup of G, which we can, a specific choice is the intersection of the unitaries, if G is in GL and C. Now this group is, this quotient group is finite. A way to show this is that the Lie algebra of this group is the same as the Lie algebra of this group. So the quotient has trivial Lie algebra, and it's also a compact group, and a compact group with trivial Lie algebra is finite. And the action that we had by the normalizer of A in K on these representations of M and A, here I've written the unitary representations of A. Of course, I'm also allowing non-unitary representations of A, so limitations are quite correct. It descends to an action by W because this thing we're quotienting by acts trivially. In the case of the representation of A, this is immediate, and this is an equality on the nose, as they say, because M centralizes A. So conjugating by an element of M, in particular the intersection of M with K, the conjugation by that is really the trivial action of A, and therefore if you define the action like this is really just the same as A, and you do exactly nothing. In the sigma case, they're only equivalent. Equivalent, but not exactly literally equal. This will play a small role later. So if K is inside the intersection, so in particular it lies in M, then this representation you get by conjugating by an element of M. And that's equivalent to the original representation sigma. And the equivalence, the intertwining operator is now sigma of K, intertwines these two operators, these two representations. So that's because K lies in M in that case. Right, so there's a finite group acting on these representations. Okay, now I'll define some intertwining operators that were constructed by Knapp and Stein in the 1980s. We saw this notation before, n bar. So we've picked an n component of our parabolic. N bar means you apply the conjugate transpose inverse to all those matrices in n, and then you get a different choice of n, which you call n bar. Now, if we have, so we look at this induced representation space, we pick an element F, and again we pick an element W in this normalizer, then the action, if the interval converges, which it doesn't always, there's an operator AP, depending on this W, sigma, and pi, which acts like this. So here we take n bar intersected with this conjugation. There's a certain measure on that intersection, and we average f from the right with respect to that measure. This doesn't always converge, but if you formally manipulate this, you expect that this would be an intertwining operator. I'll come back to this in a few slides. So whenever this integral converges, this is the definition of this A sub p, which acts on elements of this induced representation defined by sigma and mu. And the result by Knapp and Stein is that this converges for f, at least in a dense subspace of this representation space, if this psi, which determines mu, has large enough real part. And this is why we need to go beyond unitary representations nu, because if the real part of sigma is not zero, then mu is not unitary. So we need to allow large real parts for this integral to converge. And the exact condition is that, well, I'm not even saying it exactly, but the largeness of the real part means the inner product with a certain subset of the positive restricted roots used to define n has to be big enough. And then this integral converges. But this expression extends in psi, which psi is basically mu, in a meromorphic way. So you can extend it to all the mu's apart from where the poles are. In this meromorphic continuation, we'll need to get rid of those poles, and that is done by normalizing these intertwining operators. There's much you can say about this, which I won't do, but I will use the curly A to mean this normalization of this AP, where we multiply this meromorphic continuation by another meromorphic function in psi, which exactly cancels out those poles in the meromorphic continuation, so that this becomes holomorphic as a function of psi. And when we've done that, we can really plug in any mu here, including the unitary ones, and that's what we care most about. So it's a three-step process. We define AP by this integral whenever it converges. We extend meromorphically when it doesn't converge, and then we multiply by a factor to cancel out the poles to really get operators defined for all mu. Okay, this is just a comment I'm making, which I'm not coming back to. When I talked about the classical parabolics yesterday, I said there's a choice involved in the choice of n. So given your theta stable carton, the A and M are fixed, but n is determined by a choice of positive restricted roots. One thing you can do with intertwining operators, a version of them, is to show that what you do is independent of the choice of n. So they relate different n's to each other, like here. I won't go into this, I'll just assume from now on that the choice of n doesn't matter, but this is what you can use to prove this. Right. Now back to our intertwining operators from before. This operator, the claim is that it's a unitary intertwining operator from this representation space to this representation space where sigma and mu are acted on by this W. Okay. So the argument why this is the case, if you look at the original expression here, whenever this converges, well, first of all, it intertwines the left actions that define these induced representations, because if you put some G prime inverse here or here, of course, the expressions match up. So the fact that it intertwines the representations is immediate, at least in the cases where this expression holds. Then there's two more things to show, namely that this maps this representation space into this other representation space, which involves the transformation behavior under P. And that, again, in the case where this expression is true, is a relatively short argument involving manipulation of the H measures in the right way, making sure that everything is transformed in different measures. And finally, you have to show that it's unitary, which is also an argument involving these high measures. So at the level of this expression, that result by Knapp and Stein is a manipulation of high measures. And then the next steps are showing that these things are all compatible with the meromorphic continuation and then with this normalization procedure here. But the intuitive idea is that it comes from manipulation of integrals. So we have an intertwining operator, a unitary intertwining operator between this loose representation and the one where W acts on sigma and mu. The second property is a co-cycle-like property, which is when we have two elements of this normalizer. So what happens if you compose the two elements here? What operator do you get? We get this expression, which is what you might expect, because these APs, they all act between different spaces. But this, so this operator here maps into this space where we have W primes here. And then this one maps from those space with the W primes into the space with WW prime in those places. Now, we'll be looking at the special case where W fixes sigma and mu. If W fixes them, it looks here like we have an operator on the same representation space. And again, here, if W prime fixes sigma and mu, it looks like the composition acts, it's a homomorphism, it's multiplicative. The only small caveat is that, as I mentioned before, we're looking at cases where W sigma will be equivalent to sigma. So you have to include this equivalence map between them, which makes things slightly more complicated, but still manageable. Okay, so let's look at that case. So supposing again we have a W like this, and suppose that now W sigma is equivalent to sigma. We want to write down an explicit equivalence that intertwines the two representations, and we can do it as follows. By a short argument, the representation, which is just defined on M initially, extends to the group generated by M and W, because W doesn't lie in M, but we can extend sigma to a group containing both W and M. And then, this is immediate, once you have this, the action by W via sigma on this space intertwines these two spaces. So this gives us an explicit equivalence between those two representations. Now supposing that W sigma is equivalent to sigma and W mu is literally equal to mu, we then get this intertwining operator on the same space. So this is what I said earlier. If we expect if W fixes sigma and mu, that this intertwining operator acts on the same space, where we just have to include this equivalence between the two representations to be precise. So whenever W fixes sigma and mu, we get an intertwining operator on the same space. And we know from Schur's lemma that these intertwining operators tell us something about the reducibility of this representation. So we've constructed some intertwining operators, but we ideally would like to have all intertwining operators. And the fact that we've now found all of them is a result by Harris-Chandra, reformulated by Knapp and Stein. So as before, we have a Caspar parabolic M, and we have a representation of sigma now in the discrete series of M, and a unitary representation of mu of A. Now we look at this a subgroup of W. W is already finite. We look at a smaller subgroup of elements in W that fix mu literally and fix sigma up to equivalence. As I pointed out earlier, this intersection of K with M has this property, so it's still a subgroup. We can divide out. So now we have a finite group, and it turns out that all these intertwining operators, where W runs over this finite group, span the whole intertwining algebra on this induced representation space. So that means that we have some handle on how big that space is, and also through this co-cycle relation on what the algebra looks like. So that's useful information. In particular, it can happen that, that this group is trivial. And if this group is trivial, that means that the algebra here is trivial. And that means that this space is irreducible by Schur's lemma. So slightly more broadly, for sigma and nu as before, of course, the dimension of this space is at most equal to the number of elements in this group. It's not always literally equal. We'll see an actual basis later. This is only a spanning set so far. So yeah, the dimension of this intertwining operator space is at most the number of elements in this finite group. In particular, if this group is trivial, there's only one dimension worth of intertwining operators, and then by Schur's lemma, we get irreducibility. Okay. So this has the following immediate consequence. We define nu to be regular if it's not fixed by any non-trivial W. So W is a finite group acting in space and turns out on an open dense subset of A hat, which we identify with homomorphism space, linear space. On an open dense set, this is the case. So the nus that are fixed by some W, they form lower dimensional subspaces, and we leave them out in an open dense set. So for regular nu, by definition, this group is trivial because it was included that W fixes nu. So for a regular nu, this group is trivial, and that implies that this representation is irreducible. So now we already get that for nu in this open dense set, and for any sigma discrete series, this induced representation is irreducible. So that's an important irreducibility result for these induced representations. Okay, here's an example, a special case. So it's good to look at the boundaries of what we're talking about, which is now the discrete series, where the parabolic subgroup is all of G. So as we saw in the second lecture, for discrete series representation pi lambda, it's induced, which is now trivial from G to G, from the parabolic G itself, which is M, and the groups A and N are both trivial. And as I said in the last lecture, the induction is just doing nothing now, so pi lambda is the series representation. Now A is the zero space, and this wild group, the normalizer of A in K is now all of K. So M is all of G, so this is K, this is also K, and the wild group is now trivial. So particularly the subgroup that we want to look at, fixing sigma, and well, there's only the trivial representation of A now, that subgroup is also trivial, which is consistent with what we knew about the fact that these pi lambdas are irreducible. Just a consistency check for the discrete series, this group is trivial, and that is what we expect. At least we expected this to be trivial, but it's something stronger is true. Let's go back to our example of SL2R that we'll keep coming back to. For the principal series, we take the smallest crustal parabolic, which is the upper triangular matrices inside SL2R, where M is plus minus that entity. A is this upper triangular matrix group of positive entries, and N was now this upper triangular, strict upper triangular group. As before, we denote the trivial representation of M by sigma plus and non-trivial irreducible one by sigma minus, because there's only two irreducible representation of the two-element group here. We also fix a unitary representation of A, which is parameterized by the real line. Now, what does the wild group W look like now? So we first need to compute the normalizer of A and K. K is SO2, and A is spanned by this matrix. So the normalizer is all the k in k for which this conjugation lies inside A. This here is A. And by matrix multiplication, you see that this is either plus minus identity, which commutes with this, but also plus or minus this matrix, which maps this matrix to minus itself. So there's 4 elements of that normalizer. And we have to divide by the intersection of k with m, and that is m itself, plus minus identity, and lies inside k now. So we take this 4-element group and we divide by this 2-element group, and we get a 2-element group, where the non-trivial element is represented by this matrix here. And the action by this, as I said, conjugation by this matrix on this, maps it to minus itself. And that means that on the algebra A, the non-trivial element acts by reflection in 0. Okay, so W acts trivially on M because M is now M centralizes everything, so conjugation is always trivial on M. So this this group here is now trivial if M is non-zero because it acts by reflection in 0 on R, so it maps nu to minus nu. That's what's really happening here. Nu maps to minus nu. So if nu is non-zero, nothing is fixed, and if nu is 0, it's fixed by W. So this element, this group here has 2 elements, and we see that for nu non-zero, which is the regularity condition in this case, this representation is irreducible. From our previous result that for regular nu it's irreducible, and we now explicitly see that this group here is trivial, which implies irreducibility for nu non-zero. Now let's look at 0 nu. So the parameter 0 in R corresponds to the trivial representation of A. Then this group is a 2-element group W. And by this result by Harris-Chandra, we know that the dimension of the intertwining algebra is at most the number of elements in this group, which is now 2. So we know, because of the form of that intertwining algebra as these matrix blocks that I showed earlier, it can only be 2-dimensional if the representation has 2 inequivalent irreducible summands. So this representation can be decomposed into at most 2 irreducible tempered representations. This gives us some information already. Now, for these intertwining operators are somewhat abstract. I just want to write them down explicitly in the SL2R case. I mentioned in the last lecture that the representation space for the principal series of SL2R can be identified with L2 of R. So W is now the non-trivial element of this 2-element group. For the trivial representation of M, the intertwining operator has this form. And for the non-trivial representation of M, it has this form with an extra sign here. So this is the correspondence from the positive mu to the negative mu and vice versa. So these implement the only equivalences that exist between representations in the principal series, namely the nu and the minus nu 1 are equivalent. Okay, that's the SL2R case. Any questions so far? Okay, now we've seen lots of things about equivalences between reduced representations and reducibility of reduced representation. That allows us to classify almost all tempered representations. At the start, I mentioned 3 questions. The first one was, are the reduced representations enough to find all tempered representations? And then the second and third one were, which ones were equivalent and which ones were reducible? This is an answer to the first question. It's going to use a theorem which says, or 2 theorems. If you have a tempered representation sigma of M and unitary representation mu of A, then an irreducible summand of this induced representation is a tempered representation. We'll see later that this actually decomposes into a finite number of tempered representations. So this then says every one of those finitely many components is tempered. I've defined tempered to mean irreducible in particular. You can also define it as not necessarily irreducible representations, but I'm talking about irreducible ones. So this is this is one thing. So if we have a loose representation, the irreducible components are tempered. The converse is much deeper, that any tempered representation of G is contained in one of them for sigma and a discrete series of M and U and A hat. So this is really the important result why these induced representations allow us to classify the tempered representations of G. So by this result, we only need to look inside these. By this result, everything inside these representations is really tempered. So we only need to look at how they decompose into irreducibles and which ones are equivalent. And the equivalence follows from the Langdon's disjointness theorem, which says the following. We need to possibly consider different Castle parabolics as well. So suppose we have two of them, P1 and P2, decomposing like this. Supposing we have unitary representations, unitary representations of every M component, and then unitary representations of the A component, then the theorem says if these two induced representations have any common irreducible summand, then these two M factors are conjugated within K, and the sigma and mu components are conjugated within K. The converse is immediate, but this is the big theorem, this implication that you can only have any overlap between irreducible constituents under this conjugation condition. Now, in our approach, we choose, so here we're conjugating these M and A parts of a Castle parabolic. What we're doing is actually picking representatives of conjugacy classes, in which case this will never happen. So this is a reformulation and putting together some results we saw about reducibility and irreducibility. So we now pick a finite set of Castle parabolics coming from each conjugacy class of Cartan subgroup. So we have finitely many P's, none of them are conjugate, even within K. We let sigma run over the discrete series of the M part, and we let mu run over the regular elements of A hat. So for regularity, we know that this is irreducible. By what we've seen before, these are all irreducible, they're all tempered, and maybe not all tempered representations occur in this way, but almost every irreducible tempered representation occurs in this way. And the only equivalences between them, two of them are equivalent if and only if P1 is equal to P2, because we've picked representatives of conjugacy classes of Castle parabolics. And then the sigmas have to be related by some element of this normalizer, because here K was just an element of K. But this condition then forces, in particular this, if A1 is equal to A2, this forces K to be in this normalizer. And we know that this part acts trivially. So this is, again, this finite Lie group acting. A small comment here about the use of the word almost every. I've argued that what I say here is true for mu in this regular set, which is in a sense an open dense subset of A hat. But possibly the measure that we're using, the Plancherel measure, maybe it's singular, maybe it has some delta-like contributions on the singular set. But that's not true. So that's part of this claim. Why can we say almost every? And that's because the Plancherel measure on the dual is a function times a Lebesgue measure on A hat, which is isomorphic to Rn. So if we leave out a lower dimensional set, that really has measure 0. So that's why almost every is justified. And this is enough then to at least, we haven't seen the form of the Planck mesh yet, which is again a lot more work, but at least we've seen enough template representations to decompose L2 of G. Okay, so this is a result we've been working towards, a classification of almost all template representations. Okay, just some example here. 2 examples. Let's look at SLNC, or the complex semi-simple group. As I mentioned before, the easy thing about complex groups is that all Cartan subgroups are conjugate and all Cassel parabolics are conjugate as well. And all the parabolically reduced representations are now irreducible. I'll actually give a reason for this later. So we don't need to worry about reducibility. And the only equivalences come from actions by this group W. Now the template representation consists of unitary representations of M, unitary representations of A, divided by this group action. And now we needed a discrete series of M, but as I also mentioned yesterday, M is now a torus. So every unitary reduced representation of M is in a discrete series because it's compact. So in particular, M is a torus of the same dimension as A. So M hat is Zn for some M, and A is Rn for some M. This is very explicit in the complex case. Now the SL2R case, we can now list almost all template representations of SL2R, and they correspond to different choices of Cassel parabolics, which come from different conjugacy classes of Cartans. For the compact Cartan, which gives us the parabolic G, we get the discrete series from the first lecture. And the discrete series of SL2R were the Dn plus and the Dn minus for natural numbers n. So that gives us part of the template representations of SL2R. Then for the other Cassel parabolic, the upper triangular matrices in SL2R, we go through all representations of the discrete series representation of M, which is now only 2 of them, the trivial one and the trivial one. And mu runs over the unitary dual of A, which is the real line. But this while group action that I showed earlier maps mu to minus mu. So we only need to look at initially the non-negative ones. But for strictly positive mu, for non-zero mu, we know that the result is an irreducible representation. So if we take strictly positive mu, and we take the sigma plus and the sigma minus, we get template representations which are mutually inequivalent and all irreducible. So drawing the Dn plus and Dn minus give us pairs of points for every n. And we have 2 open half lines of principal series here. And this is almost all the template representations of SL2R. We'll see all of them at the end of the lecture. Okay, so we've now finished the classification of an open dense subset. I say open dense, but of course, as Bram pointed out, there's a topology on this dual. I'm not necessarily working with that topology, so I should maybe say almost all. So yeah, we've seen the classification of almost all template representations. I now want to look at the case where reduced representation may be reducible. So in the case where mu is singular, so we don't have this criterion for being reducible. And this will actually play a role in the description of the reduced algebra of G. Right, so as I just said, this representation is irreducible for regular mu. We'll now look at a singular case. Why do this? Well, first of all, this allows you to classify all the template representations, as Knapp and Zuckerman did, and this is useful for describing the reduced algebra and the K-theory of it, as Bram is going to show in the last lecture today. And the key concept for doing this is the R group. Okay, now what's the R group? We've seen a few slides ago, this result by Herchandra and Neppenstein, that these intertwining operators, where W runs over this finite set, span this intertwining algebra. Now, to have a more concrete description, it's nice to have a basis inside this spanning set, so we really know what the dimension is and more detailed information. And it turns out that you can find a basis doing, in a sense, the most obvious thing. What's the most obvious thing? Well, let's look at the subgroup of this W sigma mu, for which these operators are multiples of the identity. If this is a multiple of the identity, it doesn't tell you anything about how a representation decomposes into irreducibles. Also, these are of course all linearly dependent. So if we want to end up with a basis, we certainly have to remove this group because of this. And there's no useful information about reducibility in that group. The result by Neppenstein, which is quite deep, is that this really gives you a basis and also more information. The result is that the group W sigma mu is a semi-direct product of this subgroup with a certain finite subgroup R sigma mu, and that's the R groups we're talking about. And they actually were able to describe these groups pretty explicitly. Namely, they're all finite products of two element groups, Z mod 2Z, where the number of copies is at most the dimension of A. And it turns out that if you only take these intertwining operators for W in this R group, you really get a basis of the intertwining algebra. So this is a quite explicit description of this algebra here, in particular because, as I mentioned, we have this co-cycle relation for these things, so that also tells you something about how they compose. So that tells you a lot about what this algebra really looks like, and in turn, how this representation decomposes into irreducibles. Okay. One consequence is that for sigma, I think I said, yeah, I've said that sigma is in the discrete series, right? Yeah, sigma is in the discrete series here. Okay, so for sigma in the discrete series of M and the unitary representation of A, it follows from the previous slide that this algebra is commutative. And we know that this was a direct sum of matrix algebras, which is only commutative if those matrix algebras are one by one. So that tells us something about how often every irreducible summand occurred, namely once. This almost follows directly from commutativity of R, because we know that the elements for W inside this group, they span this intertwining algebra. And by this co-cycle condition, these intertwiners almost commute. We know that W and W prime commute. The only thing that is not quite trivial is that you have to include the sigma W and sigma W and sigma W prime, which are the equivalences between sigma and W acting on sigma. We have to take them into account, so there's a few extra arguments involved that don't immediately imply that this algebra is commutative, but that turns out to still work. So taking these sigmas into account and using a relation of this type, you can show that this is a commutative algebra. And we know the dimension, so then we know quite a lot. So here's a corollary, which is why the previous result is called the multiplicity 1 theorem, is that this induced representation decomposes into all inequivalent tempered irreducible representations, and the number is the number of elements in this R group. So we've seen that this is commutative on the previous slide, and it's a sum of matrix algebras, which implies all the MJs have to be 1. And these MJs were the number of times that the jth irreducible summand occurs. And that means we had something of this form, where all the PJs were inequivalent. So this also keeps track of how often every inequivalent representation occurs. I think there is a question in the chat. And somehow it won't let me see. Oh yeah, it is. Sigma W. Yes, we go back to sigma W. Where were we? Yeah, here. So if W sigma is equivalent to sigma, then this lemma said that the representation sigma of M extends to a bigger group that includes W, because W doesn't lie in M. And then sigma W is this extended representation as a map from the representation space of sigma to itself. And this is this map intertwines representation sigma and W sigma, because this is an explicit intertwining map between those two representations. We know here that there is an abstract unitary equivalence between the two, intertwining unitary operator. And this is just an explicit choice of that operator. And the intertwining operators on this space itself have to include this sigma, because we have to include the equivalence to map back into sigma. Does that answer the question? Okay. So the intertwining operators of sigma composed with these intertwiners A, J. Okay, so back to this multiplicity 1 theorem. We saw that the algebra is commutative and equals sum of matrix algebras, therefore all the MJs are 1. Therefore every one of these inequivalent summons occurs exactly once. And we also know how many occur because the dimension of this algebra is the number of elements of this R group. We just worked out here, so K, the number of different inequivalent summons, this should be a K here. Because MJ is 1, it equals this, and this is exactly the dimension of this algebra, and the dimension is equal to the number of elements of R sigma. So now we know, if we know the R group, we know how this decomposes into irreducibles. One separate theorem that's interesting to mention is that for a Castro parabolic that comes from a maximally compact Cartan, so the component of the Cartan subalgebra in K is as large as possible, then the R group is trivial. And if the R group is trivial, that means all these new representations are irreducible. In particular, for the discrete series that comes from a compact Cartan, which is particularly maximally compact, this is again consistent with the fact that for the discrete series, this representation is irreducible. Also, in the complex case, there's only one conjugacy class of Cartans, so they're all equally compact. So in the complex case, this immediately implies that all these representations are irreducible. Also already for compact groups, all Cartans are compact. So this is really a very explicit reflection of the fact that the complex and compact cases are easy because they only have one conjugacy class of Cartans. So for those cases, all the R groups are always trivial. So this is really, these R groups really come into play when you look at more than one conjugacy class of Cartans. Okay, some examples. Principal series of SL2R. Now the spherical principal series were the ones where the representation of M is a trivial one. So again, we have P is the upper triangular matrices in SL2R. You can explicitly show that this loose representation is irreducible. You can prove by the explicit formula for this representation I gave in the last lecture that all the I guess we would need a G invariant here, that any intertwiner can only be a multiple of the identity, which implies it's irreducible. And of course, we knew that for For non-trivial representations of A, it's also irreducible because it's regular. So knowing that from implicit computations, we know that the R group has to be trivial because that's the number of irreducible components of that representation. And therefore, W sigma 1A is W sigma 1 sigma plus prime. I hope this is readable. And this is the two-element group. So because this is now, the R group is trivial, that means that this prime group is Z02Z. In a sense, I'm cheating a bit here. I'm using the fact that we know the representation and we can explicitly compute it's irreducible, and therefore the R group is 0. Of course, in general, you would look at this group and look at which of those intertwiners are actually multiples of the identity, which gives you information about R, which gives you information about the reducibility of the representation. But here we know the representation explicitly. Now the non-spherical principal series. So that's the case where we have non-spherical means we use sigma minus. Right? The representation space is again, it can be identified with L2 of R, but now we can decompose it into two irreducible, two invariant subspaces. And V plus, to be precise, is the restrictions to real numbers of the continuous extensions of holomorphic functions on the upper half plane for which this is finite. Just to be explicit, for instance, V minus is the complex conjugates of those functions. And it turns out that these two subspaces are invariant under the action by this non-spherical principal series representation of SL2R. So again, cheating a bit and going the other way, we know already how it decomposes. Looking at this representation, we see that this decomposes into at least two irreducible factors, but we already saw earlier that it also decomposes into at most two irreducible factors. That's the number of elements of this group, W sigma nu. So now we know that the number of irreducible components is 2, which means the R group has 2 elements, and that means the W sigma group is trivial. And this now allows us to list all the attended representations for SL2R, which is one of the goals of these lectures. We've seen the discrete series. We saw that both the spherical and non-spherical principal series for positive nu were irreducible and inequivalent. For the spherical principal series, we saw that the nu equals 0 factor is also irreducible. But for the non-spherical principal series, which is this, we saw that the nu equals 0 component decomposes into two sub-representations, which are inequivalent and tempered and irreducible. And those give us two extra representations, which are called the limit of discrete series, limits of discrete series of SL2R. And now between these representations, there are no equivalences, and these are all the tempered representations of SL2R. Here's a picture. So we have the discrete series dn plus dn minus. We have the principal series, which is, here we have the spherical one, which is a closed half line. Here we have the non-spherical principal series, where the nu equals 0 component. So this is nu greater than 0, and this line here is nu equals 0. The nu equals 0 component decomposes into two irreducible summands, which are the limits of the discrete series. And Bram mentioned the topology on this space. In general, for locally compact group topology is T0. For these groups, it's actually T1, but not Hausdorff. Because as you go down here, the limit both equals this and this. So topologically, this component is what you get by taking two copies of the closed half line and then defining their interiors for corresponding points. So you get 2 points at the end. It's T1 because if you have this point, you can pick an open neighborhood of it, which doesn't include the other point, but any other open neighborhood of this point will intersect your open neighborhood, so it's not Hausdorff. And here, I think it's really interesting that, as Bram said, describing this as a topological space can be done effectively by studying the reduced C-star algebra, where the non-commutativity of the C-star algebra will turn out to correspond to the non-Hausdorffness of this component, which we'll see in Bram's lecture. Okay. For a general semi-simple G, all the template representations were classified by Knapp and Zuckerman. This involves.
Can I interject? A very naive question. The limit of discrete series, from what it looks like, it's more of a limit of non-spherical principal series. Why is it discrete series? It's the limit is called.
This is because you can describe these. The way I've described them now is coming from the minimal parabolic, and as you said, as limits of the principal series. You can also somehow associate them to the maximal parabolic G, in which case there is a notion called coherent continuation of representations. It means you have a set of representations, you make more of them. If you apply coherent continuation to the discrete series of G, then you also get these. So this is actually important also for the description of the C-star algebra and for K-theory. These two representations can come from, you can obtain them in two different ways, either by continuously extending the principal series or by coherently continuing the discrete series, if that somehow answers your question.
Yes, but the coherent continuation business you're talking about, that's not, is it compatible with the topology here?
No, the continuation is not continuous. So it's an unfortunate clash of terminology. It's a coherent extension is maybe a better word.
Thank you.
So because this is really discrete in the topology, so it's not continuity. So for the complete classification, just saying what other ingredients are needed. You need R groups, as we've seen. You need the general notion of limits of discrete series, which is defined by this coherent continuation, as I just mentioned. And then a third ingredient in the statement is induced representations with non-degenerate data, which involves information about the root system. And if you have these things, you can formulate an exact classification of all the template representations. Okay, this finishes what I wanted to say. Right. So why is it good to classify these? Well, as I said in the first lecture, if you know how to classify template representations, this allows you to classify admissible representations, and it gives you a place to look for unitary representations. So that fits into a bigger picture of representation here. Because otherwise, if you have almost all of them are enough to describe the Panchel formula. So what Knapp and Zuckerman did is classify a set of measure 0, but that's important for the admissible ones and also for the description of C-star groups of G. I'm finished. I wanted to mention very briefly some things that maybe Bram will use in the description of the C-star algebra. Just quickly. For partial parabolic P, I'll write W sigma prime, and R sigma for those corresponding groups where the representation of A is trivial. And via the compact picture of loose representations, we can realize these representations on a Hilbert space independent of mu, meaning this one. So we call that the sigma space. In the description of this reduced C-star algebra, certain group actions are used by the W sigma group and the R group. This first one may not play an explicit role. Maybe I'll skip this one because it probably won't be used. This will play a role where the R group acts on the algebra of continuous functions vanishing at infinity, on the quotient of A by this group, with values in the compact operators on the L2 space of R sigma. So R sigma is finite, so this space is finite dimensional in the complex of the matrix algebra. And it acts by, so this R sigma acts by the adjoint action on this component here, which preserves this descends to this quotient, and on this compact operators it acts by conjugation by the left regular representation by W. And this action is an ingredient in the description of the C-star algebra. And just a final comment is that the case where this W sigma prime group is trivial, so where the R group is everything, is all of W sigma, the action by this R sigma on the space A can be described explicitly. So R sigma is now this many copies of Z mod 2, where A max, this is confusing possibly, but A max is the smallest possible A that occurs. Why do you call it max? That's because it corresponds to the largest possible parabolic. And then this product of copies of Z mod 2 acts on the first so many coordinates in A, which is just, you can identify it with Rn for some n, and this acts by reflections, commuting reflections in the first so many coordinates. Very explicit way of describing this action. All right, so some comments that may be used in the description of C star boost of G, and that is it. So this is just a summary. We've classified the Lambert representations in terms of a discrete series of subgroups, parabolic subgroups, induced representations, and then testing for irreducibility using intertwines and R groups. Okay, that was it. Sorry for going over time a little bit.
All right, thank you very much, Peter. Any comments or questions to Peter? There's a question. Does adjoint of these intertwining operators exist?
I'm going to open the chat, but the window is... So the intertwining operators are unitary. So they're bounded, yeah, so they're adjoints. Oh, yeah, so the adjoints are their inverses. So the answer is yes. I'm sorry if I understand your question correctly. Does that answer the question?
I'll get feedback soon. Feel free to also turn on your cameras and just how would the parameters change?
Right. So you'd have to put the right W in to make it consistent. So we can probably reconstruct this. So we have AP W sigma mu going from to so the operator in the reverse direction you then get by taking W inverse. So AP W sigma mu star is the same as the inverse, which would be, I think I'm saying this correctly, this. Does that make sense? I'm using the co-cycle condition here as well, the way they compose. The inverse is really this. Okay.
Any other questions? All right, then I'll thank you again, Peter. So we can stop the recording.